Welcome to this problem-solving session. Today, we'll tackle an exciting coding challenge, problem number 5, longest palindromic substring. Get ready to dive into the concepts and approaches used to solve this problem step by step. Let's begin. The task here is to identify the longest palindromic substring in a given string, S. A palindrome is a sequence of characters that reads the same forward and backward. For example, the string ABA is considered a palindrome because its reverse is the same as the original. On the other hand, ABC is not a palindrome because reversing it gives a different string. Your goal is to analyze the input string and return the longest substring that satisfies this property of being a palindrome. If there happen to be multiple substrings of the same maximum length, it's okay to return any one of them. The input will always be a string composed of lowercase and uppercase English letters, and you're expected to return a single string as output, representing the longest palindrome you found. To better understand the problem, let's look at a few examples. In the first example, the input string is babid. One possible output is bab, which is a palindrome because it reads the same forward and backward. However, there's also another valid answer, ABA, as it is another palindrome of the same length. This means when multiple answers exist with the same maximum length, you can return any one of them. In the second example, the input string is CBBD. The output in this case is BB, which is the longest palindromic substring available. It's important to note that the solution must identify the longest valid palindrome, even if it has repeated characters. Now for some additional examples. Suppose the input string is just a single character, like a. In this case, the output is simply a, because a single character is always a palindrome by definition. Similarly, if the input is a string like AC, where there are no palindromic substrings longer than one character, you can return either A or C. Both are valid answers since they are single-character palindromes. These cases highlight that even the smallest substrings, when valid, must be considered. Finally, let's review the constraints and edge cases you should consider while solving the problem. The string length will range from 1 to 10,000 characters, so your solution must be efficient enough to handle very large inputs. Additionally, the input only consists of English letters in both lowercase and uppercase, meaning case sensitivity is important. For example, AA is not a palindrome. Some edge cases include strings with all identical characters, like AAA, which should return the entire string as the palindrome. On the other hand, strings like ABCD, where no two adjacent characters match, would require you to return any single character as the result. Lastly, ensure that your approach works for both short strings and very long ones without excessive time or memory usage. To solve the longest palindromic substring problem, one approach we can consider is the brute force method. This involves examining all possible substrings of the input string to determine if each one is a palindrome. For every palindrome we find, we keep track of the longest one encountered so far. The steps are straightforward. First, we generate all possible substrings, then check each substring by comparing its characters from both ends to see if it reads the same forward and backward. Finally, we update our maximum length palindrome whenever we encounter a longer one. However, this method has significant drawbacks. The time complexity is O(n) cubed, because generating all substrings takes O(n) squared, and verifying each one as a palindrome requires an additional O(n) time. Additionally, the space complexity is O(1), but the inefficiency of the time complexity makes it impractical for larger strings, especially in competitive programming scenarios. A more efficient solution is the dynamic programming approach, which uses a two-dimensional table to store results for smaller substrings and builds up to larger ones. In this approach, we define a table dp where dp, I, j, is true if the substring from index I to j is a palindrome. This method is based on a few key observations. First, a single character is always a palindrome. Second, a substring of length 2 is a palindrome if both characters are the same. And third, for substrings longer than 2, we check if the first and last characters match and if the substring between them is already marked as a palindrome in the table. To implement this, we initialize the table, marking all single character substrings as palindromes. Next, we handle substrings of length 2 and then iteratively expand to longer substrings, updating the table based on these rules. Throughout the process, we track the longest palindrome and its position. While this approach significantly improves time complexity to O(n squared), as we only need to fill the table, it does require O(n squared) space to store the table. One drawback of the dynamic programming approach is its high memory usage due to the two-dimensional table, which can be a limiting factor for very large input strings. To address this, we can use the expand around center approach, which is more memory efficient. This method takes advantage of the fact that a palindrome mirrors symmetrically around its center. By expanding outward from every potential center, we can find the longest palindrome substring. The key observation here is that there are at most 2n1 possible centers in a string, n single characters and n1 pairs of adjacent characters. The steps involve iterating through all these centers and expanding outward as long as the substring remains a palindrome. During this expansion, we compare the current palindrome's length to the longest one found so far and update accordingly. This approach avoids the need for a table, focusing solely on the structure of palindromes. The expand around center approach has a time complexity of O(n squared), as each center requires at most O(n) expansions in the worst case. However, its space complexity is O(1), as it does not require additional storage structures like the dynamic programming table. This makes it significantly more memory efficient. Another advantage of this method is its simplicity. It is easier to implement and debug compared to dynamic programming. While it shares the same time complexity as the DP approach, its lower memory requirements and straightforward logic make it a very appealing solution for this problem. Ultimately, the expand around center approach is chosen for its balance between simplicity, efficiency, and low memory usage. Unlike the brute force method, it avoids the impractical O(n cubed) runtime, and compared to dynamic programming, it eliminates the high space complexity of the 2D table while maintaining the same O(n squared) time complexity. This approach directly focuses on the structural properties of palindromes, making it both intuitive and efficient. However, like all O(n squared) solutions, it may still struggle with very large inputs. Additionally, while the logic is simpler than dynamic programming, some may find it slightly less intuitive at first. Overall, this method strikes an excellent balance, offering a practical and effective solution to the problem. To solve the problem of finding the longest palindromic substring using the brute force approach, we start by understanding what a palindrome is. A palindrome is a sequence of characters that reads the same forward and backward. For example, racecar is a palindrome because it is symmetric, but hello is not. The objective here is to identify the longest substring within a given string S that meets this definition. The brute force approach involves examining all possible substrings of the input string and verifying if each one is a palindrome. Though this approach is not efficient, it ensures completeness, meaning no potential palindromic substring will be missed. To implement this, we begin by generating all possible substrings. First, we iterate through all possible starting indices I of the string, ranging from 0 to the length of the string -1. For each starting index, we then iterate over all possible ending indices j, starting from I and going up to the end of the string. Using these indices, we extract the substring s, I, j plus 1, for further examination. Once we have generated a substring, the next step is to verify whether it is a palindrome. To do this, we compare the first and last characters of the substring. If they match, we move inward, comparing the second character with the second to last character, and so on. If all corresponding pairs of characters are equal, then the substring qualifies as a palindrome. While doing this, we also need to keep track of the longest palindrome encountered so far. For this, we use a variable max_length to store the length of the longest palindrome, and another variable, longest_palindrome, to store the actual substring. Each time we identify a palindrome, we calculate its length and compare it to max_length. If the new palindrome is longer, we update both max_length and longest_palindrome accordingly. After we have checked all substrings, the value stored in longest_palindrome will be the result, which we return as the solution. This brute force algorithm relies on an exhaustive search to guarantee that we find the longest palindromic substring. By systematically generating and checking every possible substring, we ensure that no potential palindrome is overlooked. The process of checking whether a substring is a palindrome is efficient in itself, as we only need to compare characters from both ends inward due to the symmetry property of palindromes. However, the overall approach is computationally expensive. The time complexity is proportional to the cube of the input size, or O, n cubed, because we first generate all substrings using nested loops, and then perform a nested loop within each substring to check for symmetry. As for the data structures used, we primarily rely on strings to represent both the input and substrings, along with simple variables like max_length and longest_palindrome to keep track of the results. Although correct, this method highlights opportunities for optimization, especially in reducing the number of redundant substring checks. Analyzing the complexity of this brute force approach further, the time complexity stems from two main operations: generating all possible substrings and checking each one for palindrome properties. Generating substrings involves two nested loops, resulting in O, n² iterations. Checking whether a substring is a palindrome requires comparing up to n characters in the worst case, giving us an additional O, n factor. Multiplying these together results in a total time complexity of O, n cubed. On the other hand, the space complexity is minimal because we only use a constant amount of additional space for variables like max_length and longest_palindrome, making it O1. When working with this algorithm, it's essential to consider edge cases. For instance, if the input string is empty, the result should simply be an empty string. A single character string is inherently a palindrome. If all characters in the string are identical, the entire string forms the longest palindrome. Lastly, if no substring longer than one character qualifies as a palindrome, then any single character from the string can be returned as a valid result. To solidify our understanding, let's walk through an example with the input string s equals babad. First, we generate all possible substrings, such as b, ba, bab, baba, babad, ab, aba, abad, and so on. Next, we check each substring to determine if it is a palindrome. Among the substrings, b, bab, aba, and d are identified as palindromes. While tracking the longest palindrome, we compare the lengths of these palindromic substrings. Both bab and aba have a length of 3, which is greater than any other palindrome found. Since both are valid answers, we can return either one as the result. In this case, the output is bab, though aba would also be correct. This example demonstrates the process of generating substrings, verifying palindromes, and updating our result to ensure we return the longest palindromic substring. This implementation solves LeetCode problem number 5, longest palindromic substring, using the expand around center approach, which is both time efficient and easy to understand. We start by checking edge cases. If the string is empty or has only one character, it is returned as the result since any single character is inherently a palindrome. Next, we initialize two variables, start to track the starting index of the longest palindrome and max_len to store its length. The core of the algorithm lies in the expand_around_center helper function. This function expands outward from a given left and right index, checking if the characters are equal while staying within bounds. It stops expanding when the characters differ or the bounds are exceeded. The function returns the updated bounds of the palindrome. The main loop iterates through each character of the string. For each character, we consider two cases. 1. An odd-length palindrome, centered at a single character. 2. An even-length palindrome, centered between two adjacent characters. For each case, we compute the bounds of the palindrome using expand_around_center. If the length of the new palindrome exceeds the current max_len, we update start and max_len accordingly. Finally, we extract the substring corresponding to the longest palindrome using the start index and max_len and return it as the result. The time complexity of this approach is O, n², where n is the length of the string, as each expansion takes linear time. The space complexity is O1, since no additional data structures are used, making this solution efficient and optimal for the problem. Here, we start with the definition of the method longest palindrome, which is designed to find the longest palindromic substring in a given string S. The first step is to handle edge cases. If the input string is null or its length is less than 2, we simply return the string since it's already the longest palindrome. Next, we initialize two variables, start to track the starting index of the longest palindrome and max length to keep track of its length. We then use a for loop to iterate through each character in the string. For each character, we attempt to expand outward to find palindromes centered at that index. This is done for both odd-length palindromes, where the center is a single character, and even-length palindromes, where the center is between two characters. To achieve this, we call the helper method expandAroundCenter, passing the string and the indices for the center. After checking both odd and even cases, we update start and max length whenever we find a longer palindrome. This ensures that by the end of the loop, start and max length represent the indices of the longest palindromic substring found so far. Finally, we return the substring using these indices. Now, let's look at the expandAroundCenter method, which plays a crucial role in finding the boundaries of a palindrome centered at given indices. This method takes the string s and two pointers, left and right, which represent the potential center of the palindrome. Inside the method, we use a while loop to expand outward as long as the characters at the left and right pointers match, and the pointers remain within the bounds of the string. Each time we find a match, we decrement left and increment right to continue expanding. Once the loop exits, it means we can no longer expand the palindrome. At this point, we return an array containing the adjusted boundaries of the palindrome, which are left +1 and right 1. These indices represent the inclusive start and end positions of the palindrome and the string. This helper method allows us to efficiently locate palindromes of both odd and even lengths and is called repeatedly in the main method to evaluate all potential centers. To solve the problem of finding the longest palindromic substring, we start by initializing two variables, start, which tracks the starting index of the longest palindrome found so far, and max_len, which stores its length. We also define a helper function called expand_around_center to efficiently check for palindromes by expanding outward from a given center. Now, we iterate through each character in the string. For I equals 0, we first check for odd-length palindromes by calling expand_around_center, 0, 0. This expands around the character b, and since it's a single character, the result is left 1 equals 0 and right 1 equals 0. Next, we check for even-length palindromes by calling expand_around_center, 0, 1. Here, no match is found, so the result is left 2 equals 1 and right 2 equals 0. Based on these results, we update max_len to 1 and start to 0. Moving to I equals 1, the odd-length check with expand_around_center, 1, 1, expands around it and matches the substring bab, resulting in left 1 equals 0 and right 1 equals 2. The even-length check with expand_around_center, 1, 2, results in no match, leaving left 2 equals 2 and right 2 equals 1. Here, we update max_len to 3 and start to 0. At I equals 2, the odd-length check with expand_around_center, 2, 2, expands around b, matching the substring ABA, with left 1 equals 1 and right 1 equals 3. The even-length check with expand_around_center, 2, 3, finds no match, resulting in left 2 equals 3 and right 2 equals 2. Since the length of the new palindrome is not greater than the current max_len, no update is made. For indices I equals 3 and I equals 4, similar checks for odd and even length palindromes are performed, but no longer palindromes are found. At the end of these iterations, the longest palindrome identified is the substring starting at index 0 with a length of 3. Using these values, we return the substring s, start plus max_len, which is bab. Now, let's explore a second example with the input string s equals cbbd. We begin by initializing start equals 0 and max_len equals 0. At I equals 0, the odd-length check with expand_around_center, 0, 0, expands around c, resulting in left 1 equals 0 and right 1 equals 0. The even-length check with expand_around_center, 0, 1, finds no match, with left 2 equals 1 and right 2 equals 0. We update max_len to 1 and start to 0. Next, for I equals 1, the odd-length check with expand_around_center, 1, 1, expands around b, resulting in left 1 equals 1 and right 1 equals 1. The even-length check with expand_around_center, 1, 2, matches the substring bb, with left 2 equals 1 and right 2 equals 2. Here, we update max_len to 2 and start to 1. For indices I equals 2 and I equals 3, similar checks are performed, but no longer palindromes are found. At the end of this process for the second example, the longest palindrome identified is the substring starting at index 1 with a length of 2. Using these values, we return the substring s start plus max underscore len, which is bb. Finally, let's consider the third example where the input string is s equals a. Since the string contains only one character, we initialize start equals 0 and max underscore len equals 0. For I equals 0, the odd length check with expand underscore around underscore center 0, 0 expands around a, resulting in left 1 equals 0 and right 1 equals 0. The even length check with expand underscore around underscore center 0, 1 finds no match, with left 2 equals 1 and right 2 equals 0. Here, we update max underscore len to 1 and start to 0. With only one character in the string, the longest palindrome is simply the character itself. Thus, we return s start plus max underscore len, which is a. Now, let's analyze the time complexity of this solution. The outer loop iterates through all indices of the input string, s, so it runs in O, n, time, where n is the length of the string. Within each iteration of the outer loop, we call the expand underscore around underscore center function. This function checks for palindromes by expanding outward from a given center. In the worst case, this expansion continues until we hit the boundaries of the string or find a mismatch, which means it takes O, n, time for a single call. Since this function is called twice per iteration, once for odd-length palindromes and once for even-length palindromes, the total time spent in expand underscore around underscore center for one iteration is O, 2 asterisk n, which simplifies to O, n. Combining the O, n, iterations of the outer loop with the O, n, time spent per iteration in palindrome expansion, the total time complexity is O, n, asterisk O, n, which results in O, n squared. Even when we consider different scenarios, the time complexity remains O, n squared. In the best case, such as when all characters in the string are distinct, the algorithm still needs to check all potential centers, which confirms the O, n squared, complexity. In the worst case, like a string with all identical characters, such as AAAA, the expansion for each center will extend to the full length of the string, again leading to O, n squared. On average, the nested nature of the palindrome expansion process dominates the runtime, so the complexity remains O, n squared, overall. Now, let's consider space complexity. The algorithm uses only a constant amount of extra space. Variables like start, max underscore len, left, and right require O1 space. Additionally, the expand underscore around underscore center function operates in place, modifying the left and right pointers directly without allocating extra memory. This means the space complexity is O1. The solution does not use any additional data structures such as arrays, lists, or hash maps, which means no extra memory is allocated beyond the fixed variables already mentioned. As a result, the total space complexity remains O1. Let's compare this optimized solution to a naive approach. The naive method involves generating all possible substrings of the input string and checking each one to see if it's a palindrome. Generating all substrings takes O, n squared, time since there are n asterisk, n plus 1, / 2 substrings. For each substring, checking whether it's a palindrome takes O, n, time in the worst case. This results in an overall time complexity of O, n squared, asterisk O, n, which simplifies to O, n cubed. Additionally, the naive approach requires O, n squared, space to store all substrings. Compared to this, our current solution is significantly more efficient in both time and space complexity. By leveraging the center expansion technique, the optimized solution reduces the time complexity to O, n squared, while maintaining a space complexity of O, 1. This is a substantial improvement over the naive approach, especially for large input strings. To summarize the mathematical reasoning behind the time complexity, the outer loop runs n times, and for each iteration, the palindrome expansion checks at most n characters in the worst case. This results in a total of n asterisk n operations, which simplifies to O, n squared. The space complexity, on the other hand, is constant because no additional memory scales with the size of the input. Therefore, the overall complexity of the solution is O, n squared, 4 times n O, 1, for space, making it a highly optimized approach for solving the problem of finding the longest palindromic substring. When working on the longest palindromic substring problem, there are several common mistakes to watch out for. First, it's crucial to understand the problem constraints. For example, if the input size is very large, such as n greater than 10 to the power of 4, a brute force solution with O, n cubed, complexity will be far too slow. Instead, you should analyze constraints to determine an efficient approach. Another common issue is neglecting edge cases. These include scenarios like single character strings, strings with 2 characters, or even strings that don't contain any palindromes at all. Neglecting these can lead to bugs in your implementation. Additionally, when extracting substrings in Python, it's easy to make off-by-one errors with slicing, so always verify your n+1 logic. Finally, while dynamic programming can be intimidating, skipping it entirely can be a missed opportunity, as it provides significant runtime improvements for this type of problem. Another frequent mistake is misunderstanding the properties of a palindrome. Remember, a palindrome reads the same forwards and backwards, so your checks must adhere strictly to this definition. Now, when it comes to interviews, there are important patterns to identify. Substring problems often involve techniques like sliding windows, dynamic programming, or 2-pointers. Recognizing symmetry in the problem, such as the nature of palindromes, can dramatically simplify your approach. For example, center expansion is a highly efficient and intuitive method to solve this problem, as it avoids unnecessary computations while being straightforward to implement compared to dynamic programming. Interviewers will also evaluate how you balance trade-offs between brute force, dynamic programming, and other optimized solutions. They value clarity in explaining your decisions, handling edge cases, and structuring your code logically, especially when tackling recursive or more complex implementations. This problem is often related to other challenges that test similar skills. For instance, problems like palindrome partitioning, valid palindrome, and longest palindromic subsequence all build on the same foundational concepts. Understanding these related problems can deepen your knowledge of the topic. Now, let's discuss alternative approaches and their trade-offs. Brute force, for example, has a time complexity of n cubed. While it's straightforward to implement, it's impractical for larger inputs because of its inefficiency. On the other hand, a dynamic programming solution reduces the time complexity to n squared. This approach is more efficient for medium-sized inputs, but it does come with higher space requirements compared to methods like center expansion. Each method has its place, and understanding these trade-offs is key to selecting the right approach for a given situation. Center expansion is another popular and efficient technique for solving the longest palindromic substring problem. Its time complexity is n squared, but it only requires 1 space, making it optimal in both time and space efficiency. However, it may be slightly less intuitive than dynamic programming for some, as it relies on identifying and expanding around potential palindrome centers. For those aiming for maximum efficiency, there's also Manicher's algorithm, which reduces the time complexity to n. While it's extremely fast, the trade-off is its complexity. It can be challenging to understand and implement, and it's rarely necessary in standard interviews unless explicitly requested. Ultimately, for most interview scenarios, center expansion strikes the best balance between simplicity and efficiency, making it the preferred choice in many cases. Great work! To recap, we explored the problem of finding the longest palindromic substring and discussed various approaches. Remember the key takeaways, and apply these techniques in your practice. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!